this lecture. We had a very basic understanding about framing, and in today's session we will formally see what is framing. We will start the session with the outcomes. In today's session we have 3 outcomes. We will see what are they one by one. Upon the completion of the session, the learner will be able to: outcome number 1, understand the basics of framing formally; outcome number 2, understand the types of framing; and the last outcome, we will know various framing approaches. We will start the session with what is framing. We know framing is one
What the hell?
of the services of the data link layer, and if we say there are 2 nodes, and these 2 nodes will obviously have adapters, and when we talk about nodes, frames are going to be exchanged. When we talk about adapters, the bits or the signals are going to be exchanged. Framing in the data link layer separates a frame distinguishable from another frame. Suppose if node A wants to send a bulk of information to node B, and this cannot be sent as a single frame, so node A creates 10 frames for example, and all these 10 frames are going to be placed on the medium, and we expect the receiver to understand that there are 10 frames. The receiver's adapter receives the continuous services of the data link layer, and if we say there are 2 nodes, and these 2 nodes will obviously have adapters, and when we talk about nodes, frames are going to be exchanged. When we talk about adapters, the bits or the signals are going to be exchanged. Framing in the data link layer separates a frame distinguishable from another frame. Suppose if node A wants to send a bulk of information to node B, and this cannot be sent as a single frame, so node A creates 10 frames for example, and all these 10 frames are going to be placed on the medium, and we expect the receiver to understand that there are 10 frames. The receiver's adapter receives the continuous zeros and ones. It becomes the responsibility of the receiver node to exactly construct the frame as like it was sent. So framing in the data link layer separates a frame distinguishable from another frame. And we know that frame means it is the network layer PDU that is additionally added with the header and the trailer of the data link layer. We will see what is the role of framing in packet switched networks. In packet switched networks, the block of data called frames are exchanged between nodes, not the bit streams. We have already seen this point. Between adapters, we see that there are bit streams, but actually between nodes, we say that there are frames that are going to be exchanged. We will also see the other aspects. Suppose when node A wants to send some data to node B, what it actually does. When node A wishes to transmit a frame to node B, it tells its adapter, that is, node A tells its adapter, this adapter, to transmit a frame from the node's memory. So the data that is received by the data link layer is ready and it is created as a frame, and it tells the adapter to place, or it tells the adapter to transmit a frame from the node's memory. So this results in a sequence of bits being sent over the link. So the sequence of bits are going to be sent over the link, and it is the responsibility of the adapter to send the sequence of bits over the link. After node A sends the data, now it's the turn of node B to deal with it. The adapter on node B then collects together the sequence of bits arriving on the link and deposits the corresponding frame in B's memory. So we know A has sent the continuous sequence of bits, and the B's adapter will receive all the sequence of bits and it stores the sequence of bits as frames in B's memory. we have a big challenge in front of us. The challenge is what sets of bits constitute a frame. It is easy for both the nodes if the frame size is fixed, because if we say 10 is the frame size, whenever it receives 10 bits, it can construct a frame and place it in the memory. Again, if it receives another set of 10 bits, it creates a frame and stores in the memory. If the frame size is fixed, it is easy. What about if the frame size is a variable size? And that is what we are going to see, the types of framing. We have basically two types of framing. One is fixed size framing. Number two, variable size framing. We will see one by one. We will start with the fixed size framing. In a fixed size framing, the sender and receiver know the size of the frame. So it is easy for the sender and receiver to construct the frame. Here, the size of the frame is fixed so that the frame length acts as the delimiter of the frame. For example, if the size is 100, after receiving 100 bits, the receiver can understand that frame 1 is collected. Then the next set of 100 bits means it is frame 2. Consequently, it doesn't require additional boundary bits to identify the start and end of the frame. Since the size itself is acting as the delimiter, it does not require any additional boundary, or it does not require to give a start of the frame or the end of the frame. There are variable size framing also. In a variable size framing, here the size of each frame to be transmitted may be different. For example, 100 bits may constitute frame number 1, 60 bits may constitute frame number 2, 80 bits may constitute frame number 3. But in this case, it's very difficult because the length is not uniform for all the frames. The size is not uniform for all the frames. So it is a must to maintain the start of the frame and the end of the frame. I hope you guys can recapture what we have seen in the previous lecture. We have seen in the previous lecture that the start of the frame and the end of the frame that helps the receiver to construct the frame. So additional mechanisms are kept to mark the end of one frame and the beginning of the next frame. So in a fixed size framing, we need not maintain any such start of the frame or end of the frame, whereas in variable size framing, we are required to maintain the end of the frame and the starting or the beginning of the frame. And this will help us to construct the frames without framing errors. And that's it about the types of framing. So far we have seen what are the basics behind the framing and the types of framing. Let's have a look at the various framing approaches. When we talk about framing, we have basically two approaches. One, it is bit-oriented approach, and number two, it is byte-oriented approach. Byte-oriented approach are also called as character-oriented approach. We will talk about this elaborately in the upcoming lectures. And that's it, guys. I hope hello everyone, and this one came under we handled this. I hope you
John the man talk. What's up? Why are you crying? No, I just woke up and I just stream. That's why. Kind of sleepy, but send link. What do you mean send link? Oh, I just start a timer. Boom. The website you're looking at? Okay. Flexing, yeah. Actually, I can just send it from here too. Gotta flex some things, man. Gotta use it wisely. I'm so hungry. I think I'll eat some. I'll drink some water then. I'm really hungry. It is helpful to first get a lay of land, which includes a wide range of land technologies instituted in part of the list. Oh yeah, let's see. Wait, no. Seems.
video, we're going to focus on a few problems that asked to find the wavelength and the frequency of a photon. So let's start with this one. Calculate the wavelength of a photon that has a frequency of 2.5 times 10 to the 12 hertz. So what equation do we need? Perhaps you've seen this one. C is equal to lambda times nu. Now C is the speed of light. Lambda represents the wavelength in meters, and nu is the frequency in hertz. So the wavelength is going to be the speed of light divided by the frequency. The speed of light, you need to know it's 3 times 10 to the 8 meters per second. Time to focus on a few problems that ask to find the wavelength and the frequency of a photon. So let's start with this one. Calculate the wavelength of a photon that has a frequency of 2.5 times 10 to the 12 hertz. So what equation do we need? Perhaps you've seen this one. C is equal to lambda times nu. Now C is the speed of light. Lambda represents the wavelength in meters, and nu is the frequency in hertz. So the wavelength is going to be the speed of light divided by the frequency. The speed of light, you need to know it, it's 3 times 10 to the 8 meters per second. The frequency is 2.5 times 10 to the 12 hertz, which is the same as seconds to the minus 1, or 1 over a second. So basically, we just need to divide these two numbers. To the minus times 10 to the 1 hertz, which is the same as seconds to the minus 1, or 1 over a second. So basically, we just need to divide these two numbers. And so you should get 1.2 times 10 to the negative 4 meters. And so that's all you need to do in order to get the answer. Now sometimes you may need to convert it to a different unit because this number is pretty small. So let's convert it to micrometers. How can we convert meters to micrometers? What is the value of 1 micrometer? Micro represents 10 to the minus 6, so 1 micrometer is 10 to the negative 6 meters. You can take this number and move it to the top by changing the exponent from negative 6 to positive 6. So this is equivalent to 1.2 times 10 to the minus 4 multiplied by 10 to the positive 6. And when you multiply by a common base, you need to add the exponents. So negative 4 plus 6 is 2. So the answer is 1.2 times 10 to the 2 micrometers. Now 10 squared is 100, and 100 times 1.2 is 120, 10 to the positive 6. And when you multiply by a common base, you need to add the exponents. So negative 4 plus 6 is 2. So the answer is 1.2 times 10 to the 2 micrometers. Now 10 squared is 100, and 100 times 1.2 is 120. So the wavelength, you could say, is 120 micrometers. So if you have a multiple choice test, your answer may be in meter. So 2 times 10 to the 2 micrometers. Now 10 squared is 100, and 100 times 1.2 is 120. So the wavelength, you could say, is 120 micrometers. So if you have a multiple choice test, your answer may be in meters, or it could be in a different unit, micrometers. So you might have some conversions with these problems as well. Just be ready for that. Now let's move on to number 2. What is the frequency of a photon that has a wavelength of 1.5 times 10 to the negative 8 meters? So go ahead and try that problem. So starting with this equal to this times 10 to the 8 meters. So 3 divided by 1.5 is 2. Now what's 10 to the 8 divided by 10 to the negative 8? When you divide by a common base, you need to subtract the exponents. So you take the top exponent, which is positive 8, and subtract it by the bottom one, which is negative 8. 8 minus negative 8 is the same as 8 plus 8, so that's 16. So the answer is 2 times 10 to the 16 hertz. So that's the frequency of this photon. Drop divided by 10 to the negative 8. So now we just got to divide these two things. Is 2 minus negative 8 is the same as 8 plus 8, so hertz. And to make sure that we do indeed have the right answer, which it is that answer. Now what about number 3? What is the frequency of a photon that has a wavelength of 350 nanometers? It turns out that if you want to write it out, here's what you can do. Start with what you're given, and know that 1 nanometer is equivalent to 10 to the minus 9 meters. So these units will cancel, and all you have is 350 times 10 to the minus 9. So you just got to replace this with 10 to the minus 9. And the speed of light is not going to pass us through it, but in pure empty space, times 10 to the 14 hertz. Seconds to the minus 1. So this is the answer for this problem. Number 4. Determine the wavelength of a photon that has a frequency of 95 megahertz. So to calculate the wavelength, we know it's the speed of light. We can make it from now. So that's the frequency of mega. A megahertz is basically a million hertz. Mega represents 10 to the 6. So what we have now is 95 times 10 to the 6 hertz. So that's the frequency. So now that we changed the unit by these, we should photon with that frequency. Now as you see in speed of seeing the lightning up relates joules simply so as the frequency increases, the wavelength decreases. And vice versa. So as the wavelength increases, the frequency decreases. So these two are always going to be inverse.
Yeah.
Related to about photons and the relationship between the wavelength and frequency of a photon. How can you calculate the frequency? The equation that relates is going to be divided by joule per second. So let's divide these two numbers.
What area? Computer network. Yeah. Basically, my major, my field of study is computer science, but I'm currently taking computer network course, so I'm just learning it right now.
So the frequency is going to be 5.28 times 10 to the 15 hertz. And so that's how you can calculate the frequency of a photon given its energy. So let's so if you negative 30 of a photon first, you can read the speed of light divided by the frequency. Determine the wavelength of a photon with an energy of 4.3 times 10 to the negative 19 joules. So what we're going to do in this problem is just like before, we're going to calculate the frequency first. And once we have the frequency, then we're going to calculate the wavelength. So the frequency is going to be the energy divided by Planck's constant. So it's 4.3 times 10 to the negative 19 joules divided by 6.626 times 10 to the minus 34. First. Once we have the frequency, then we're going to calculate the wavelength. So the frequency is going to be the energy divided by Planck's constant. So it's 4.3 times 10 to the negative 19 joules divided by 6.626 times 10 to the minus 34. So you 10 frequency is going to be the speed of light divided by the frequency. So that's 3 times 10 to the 8 meters per second divided by 6.49 times 10 to the 14 hertz. So you should get 4.62 times 10 to the negative 7 meters. Now let's go ahead and convert this to nanometers.
Minus what? Nanometer is what?
So keep in mind, 1 nanometer is equivalent to 10 to the minus 9 meters. So I'm going to take this and move it to the top. So then it becomes 4.62 times 10 to the minus 7 times 10 to the positive 9. A negative 7 plus 9 is 2. So it's 4.62 times 10 to the 2 nanometers. And we know 10 squared is 100, so 100 times 4.62.
Wait.
Is is 462 nanometers.
Let's see.
So that's the wavelength in nanometers. This is the answer.
Okay, makes sense.
session on Introduction to Network Devices, Part 2. Today,
the next thing that you would need to know to become a back-end Python developer is some basic networking skills. Now, I think you could probably get away without having this, but I would highly recommend spending a few days learning about basic networking. So learning about HTTP. What is that protocol? How does that work? How do you serve data over the web? Learning about IP addresses. Learning about, say, firewalls, learning about VPNs, and just, again, kind of fundamental things related to networking. Maybe you want to learn why localhost works the way it does, about different ports, about, kind of standard ports you'd have for a website versus ports for other services.
Hello, welcome to the first lesson in the first module of my new course on networking fundamentals. In this module,
if you want to get started in cybersecurity, A+. You to compute the CompTIA Network Plus or the Cisco requires. The coding will be a path that I would made it to the end.
What? Some way we're gonna go to my little cheat sheet here. Now, again, this is really long, so things like one right here. So what we're gonna do, actually, let's find a better one. So we're gonna
Hi guys, I'm glad you decided to join the course. In this course, we'll be learning about Python network programming and TCP IP socket programming. I'm really excited about this course because you'll be
I need to abstract.
Hey, let's talk about sockets and networking. I've been doing a lot of beginner videos lately. Don't worry. Hey everybody, we're coming to us. All HTTP. So now when we go to our hey, let's talk about sockets and networking.
What is going on, guys? Welcome to this Python course for network programming. In today's
Python is going to next networking by actually coding a reverse shell PyCharm installed. You can directly jump to
what is we're going to define the message. We're not going to use a real mail fast as possible. What is good?
feature is indeed
Hello and welcome to this 15 hour. You know, I did this. We have these 30.
get along. Resume. Glasses on.
distribution. However,
what is HTTP and why do I see it everywhere? Hypertext Transfer Protocol is a protocol used to transfer information between network devices and runs on top of other network protocol stacks. When you open up your browser and type in google.com, you're sending an HTTP request to Google servers. They read that request and then send a response. This is usually in the form of a website. This is also where you see those HTTP status codes like 404 not found or 500 server error. HTTP is over 31 years old and is the standard when it comes to using the internet. Now, how do I even fix this 404 error? What is HTTP and
हाँ जी, क्या हाल चाल है आप सबके? आई एम श्योर कि आप लोग जो बहुत ही अमेजिंग होंगे. सो गाइज, आज का जो है ये शॉर्ट जो है मैं दे रहा हूँ, इसमें आंसर और क्वेश्चन पूछा है सौरभ यादव ने.
Have you ever wanted to learn how a computer works? Raspberry Pis are microcomputers that are This will make you a genius programmer. Ever wanted to know how big tech companies
provides improved clock and data synchronization system, including
include the insertion loss from the board traces, signal reflections at the connector interfaces, and crosstalk noise from the adjacent signals. Jitter acts as a bottleneck to system speed and performance, limiting the link reach and achievable bit error rate. A system such as this enterprise switch may use multiple CDRs to restore signal integrity at different points along the data path. Systems typically target performance to industry standards at each of these signal points. Retimers are often required to meet those specifications. What function do CDRs perform in retimers? The retimer uses its CDR to sense the input data and produce a periodic and synchronized clock. This clock, recovered from the data, is then used by a sampler decision circuit. The sampler outputs a 1 or a 0 depending on its input voltage level, and its sampling of the input data is clocked by the CDR. This retiming function using a clean recovered clock allows the output to the VCR CDR.
Hey, Striker is live. Way.
In NRZ-I signal encoding, we have to start from this point and the upper point as all other NRZs, and all we have to do is we have to turn to the opposite side if we found a 1, or otherwise we won't have to do anything. If we get constantly all zeros, we have to stay on that side. So here we have 0, so we are staying here, and for this one we have to change our side, so we have to go down, and now we have zeros, so we stay here, and now we have a 1, so change.
To transmit digital data using digital signals, the ones and zeros of the digital data must be converted into the proper physical form. This digital to digital conversion is called digital encoding. So for each data bit like 0 or 1, a certain voltage level like 0 and 5 volts are usually used. The most common types of encoding are NRZL, NRZI, Manchester, differential Manchester, and bipolar AMI. These methods, especially Manchester, are mostly used in LANs and telephone systems. This picture shows these 5 types of encoding. The non-return to zero level, or NRZ, digital encoding schema transmits 1 as 0 voltage and 0 as positive voltage. The NRZL encoding is simple to generate and inexpensive to implement in hardware. The second digital encoding method, as shown in part B, is non-return to zero inverted, or NRZI. This encoding schema has a voltage change at the beginning of A1 and no voltage change at the beginning of A0. The difference between NRZL and NRZI is that with NRZL, the receiver must check the voltage level for each bit to determine whether the bit is a 0 or a 1. But with NRZI, the receiver must check whether there is a change at the beginning of the bit to determine if it is 0 or 1. Problem with the NRZL and NRZI digital encoding is that long sequences of zeros in data produce a signal that never changes, and it is going to make it difficult for a receiver machine to distinguish between 0 and 1. This problem is called synchronization issue.
To address the synchronization issue with NRZ-L and NRZ-I, the Manchester encoding was developed. With Manchester, each bit has some type of signal change, and the synchronization issue is never going to happen. In Manchester, to transmit a 1, the signal changes from low to high in the middle of the interval, and to transmit a
You've been through tough times before.
What sunshine is to flowers, smiles are to humanity.
Good evening.
I still get nightmares. I often find myself thinking about the times we spent together.
What sunshine is to flowers. The second problem is that frequent transitions from high to low and vice versa are necessary to enable clock recovery. Intuitively, the clock recovery problem is that both the encoding and decoding processes are driven by a clock. Every clock cycle, the sender transmits a bit and the receiver recovers a bit. The sender's and the receiver's clocks have to be precisely synchronized in order for the receiver to recover the same bits the sender transmits. If the receiver's clock is even slightly faster or slower than the sender's clock, then it does not correctly decode the signal. You could imagine sending the clock to the receiver over a separate wire, but this is typically avoided because it makes the cost of cabling twice as high. So, instead, the receiver derives the clock from the received signal, the clock recovery process. Whenever the signal changes, such as on a transition from 1 to 0 or from 0 to 1, then the receiver knows it is at a clock cycle boundary, and it can resynchronize itself. However, a long period of time without such a transition leads to clock drift. Thus, clock recovery depends on having lots of transitions in the signal, no matter what data is being sent.
Whenever the signal change, such as a transition from 0 to 1 or from 1 to 0,
One approach that addresses this problem, called non-return to zero inverted, has the sender make a transition from the current signal to encode a 1 and stay at the current signal to encode a 0. This solves the problem of consecutive ones, but obviously does nothing for consecutive zeros. NRZI is illustrated in figure 25. An alternative, called Manchester encoding, does a more explicit job of merging the clock with the signal by transmitting the exclusive OR of the NRZ encoded data, and the clock. The Manchester encoding is also illustrated in figure 25. Observe that the Manchester encoding results in 0 being encoded as a low to high transition and 1 being encoded as a high to low transition. Because both zeros and ones result in a transition to the signal, the clock can be effectively recovered at the receiver. There is also a variant of the Manchester encoding, called differential Manchester, in which a 1 is encoded with the first half of the signal equal to the last half of the previous bit's signal, and a 0 is encoded with the first half of the signal opposite to the last half of the previous bit's signal. Images F02-05-9780123850591.png.
the so 0, so go down and then connect them. 1 to do.
So let's say we have two computers here, and we want to send some data from one computer to the other. So if we
Arduino is an open source electronics tool, and
of course this code right to have the course or another with split is new old electron a wire like this. You can see these electrons are moving in this. Here are a few technical specifications. Now I will take video. No connection, like push button. Okay, the represents on. Now we will see some more concepts in voice. Now some of you must have next video. We will now really 750, 79, 711, 9.
Automatic watering system that also allows you to monitor what it's doing, and even manually water the system if the sensors fail. If this is content you like, please hit as I'm about to do. If you aren't familiar with what you could probably see if maybe to know. Actually have $12 battery.
seen before, we can connect a cable between them and then maybe vary the voltage across two of the wires within this cable, like say between 0 volts and 5 volts. And 0 volts is a symbol that represents a 0, and 5 volts is a symbol that represents a 1. And so we can send some binary data this way, 0, 1, 1, 0, 1. But something interesting is happening right here, which is we have a bunch of zeros in a row. And in order to know exactly how many zeros we have here, we need to make sure that both of these computers have a synchronized clock. And this is something that's actually very important in networking is timing, to make sure that both sides of this link agree on a clock rate. So if I add a clock rate here, this is a signal basically that just alternates between 0 and 1, 0, 1, 0, 1. And what we can do is we can look at this clock everywhere it transitions from 0 to 1. That is a point at which we should read the value of the data. So we have a data signal here, and we have a clock signal here. And so for this example here, where we have this whole string of zeros, if we just look at how many transitions, or exactly when these transitions occur from 0 to 1 on the clock, we can see, this transition, the data is a 1. This transition, it's a 0. This transition is another 0. This transition is another 0, another 0, another 0, and then a 1. And as long as we keep track of these transitions, we know exactly how many zeros we have, no matter how long this stretch of data is, as long as we have this clock. But the important thing is that both sides of this link agree on the same clock, so that the computer that is sending this data is using the same clock rate as the computer that's receiving it. So now you might be wondering what happens if these two computers' clock signals aren't running at exactly the same speed. So like maybe the receiver's computer is a little bit slow. So I can show you actually what that might look like if we take that out and bring this in, and I'm actually going to get rid of these little transitions. So this here is a clock that is running a little bit slower than the data was originally clocked at. And so what you see here is that here's a transition, and we get a 0, another transition, a 1, and these are actually lining up pretty well so far. So this 0 kind of is lining up. But here, you notice we missed a 0. There should be a 0 here. And then this stuff lines up pretty well. And again, we miss a 0. And then things are lining up okay. But here in this stretch where we had 5 zeros before, now with a slightly slower clock, we're only reading 4 zeros. And then we have this last one here. And so the places where we're missing bits because of this mismatch, I guess, between transmit and receive clocks are called clock slips. So this is a clock slip because we're basically missing a bit of information. And then you might have the sort of opposite of this. If the receiving clock were running faster, you might actually get extra bits in there. But either way, we would refer to that as a clock slip. So this here is a clock slip. And of course, if we're missing bits like this, then the data that we're receiving isn't going to make any sense. So clearly, we don't want the two computers' clocks to be out of sync like this. So even if they're a little bit out of sync, of course, this is kind of an extreme example here where we were sending 16 bits and we only received 13 bits. But even if these clocks are just a little bit out of sync, eventually over time we will have a clock slip. And that'll corrupt our message, and we would have to either retransmit our message or somehow figure out what happened there. So it's important to make sure that these clocks are in sync, and there are a couple ways that we can do that. One way that we can make sure that clocks are in sync is actually for both of these computers to have synchronized clocks that are either synchronized maybe through a GPS antenna. So these computers would have little antennas that would connect, or that would actually receive signals from GPS satellites, which are the Global Positioning System satellites. Because the GPS satellites actually have atomic clocks on board and have very, very accurate clocks. And so if these computers have those GPS receivers, they can synchronize their own clocks to the GPS clocks, and then know that the clocks between the two computers are in sync, and use those clocks for sending and receiving data. There's obviously some disadvantages to that. The GPS antenna is extra hardware, so it's a little bit expensive. And you also need to be able to mount the antenna somewhere outside or on the roof of the building or something like that. But there's definitely some network equipment that is in use on the internet that uses GPS timing to synchronize its clock and data. So that is one solution. Another solution is actually to have an atomic clock in the computer itself, and that's occasionally that is done. It's fairly uncommon. Another approach that you could take is get rid of our slow clock and bring back our normal clock here. Another approach that you can take is to actually send a separate signal. So we have a separate, we have like another link or another pair of wires between these computers where we send this clock signal. So we're sending both the data and the clock across two different links. And so that way, this computer doesn't need to use its own clock. It can actually receive the clock from the same computer that's sending the data. So it knows to have GPS satellites, which are the global positioning system satellites, because the GPS satellites actually have atomic clocks on board and have very, very accurate clocks. And so if these computers have those GPS receivers, they can synchronize their own clocks to the GPS clocks and then know that the clocks between the two computers are in sync and use those clocks for sending and receiving data. There's obviously some disadvantages to that. The GPS antenna is extra hardware, so it's a little bit expensive. And you also need to be able to mount the antenna somewhere outside or on the roof of the building or something like that. But there's definitely some network equipment that is in use on the internet that uses GPS timing to synchronize its clock and data. So that is one solution. Another solution is actually to have an atomic clock in the computer itself, and that's occasionally that is done. It's fairly uncommon. Another approach that you could take is get rid of our slow clock and bring back our normal clock here. Another approach that you can take is to actually send a separate signal. So we have a separate, we have like another link or another pair of wires between these computers where we send this clock signal. So we're sending both the data and the clock across two different links. And so that way, this computer doesn't need to use its own clock. It can actually receive the clock from the same computer that's sending the data, so it knows that these are in sync. And there's actually a little bit of a problem with that as well, or a potential problem with that, which is that as you increase the speed that you're sending this data, these clock pulses could actually be as close as just a few nanoseconds apart. And so it's very important that the clock and the data line up, because if you can imagine this clock were shifted just a little bit to the left or to the right, then these points where the clock transitions from a 0 to a 1 might not line up exactly with the bits, and you could misread a bit. So it's very important that these stay lined up correctly, and that's called clock phase. And one of the problems with sending a clock and a data across two separate links is that it's possible that the propagation of electrons literally across one of these links might be slightly slower, either because it takes a slightly different path or the conductivity is a little bit different if this is a long path. So you tend to not want to do this on very high-speed links over very long distances, or you could get into an issue where the clock gets slightly out of phase with the data and you start to misread some bits. So another approach that we can take that's actually quite common is kind of ingenious, which is to combine the clock and the data by using different symbols to represent ones and zeros. So just to review, what we've been doing here is when we're transmitting our data, we're transmitting it using two symbols. And so when we want to send a 1, the symbol that we're using is 5 volts. So you can see here, every time we're sending a 1, our symbol is that we are setting the voltage to 5 volts. When we want to send a 0, the symbol we use is 0 volts. So now let's see what happens when we change that. So instead, let's try to make the symbol for sending a 1. Instead of making it 5 volts, let's make it, actually the symbol will be transitioning from 0 volts to 5 volts. So this is 0 volts, this is 5 volts. And the symbol for a 1 is a transition from 0 to 5. And then what we can do is the symbol for sending a 0 will be a transition from 5 volts to 0 volts. So this was 5 volts, and we're transitioning to 0 volts. So before, the symbol that we were using was, the symbol we were using for sending a 1 is just a 5 volt signal. Now let's try sending a transition from 0 volts to 5 volts as the symbol. So what we can do is, here is that same signal right here that we were sending up here. So we can see both of these. So this is the same data, this 0, 1, 0, 0, 1, 0, and so on, is now being sent using this scheme. So for example, here we have a transition from 5 volts to 0 volts. So this is 5 volts. Oops. This is a transition from 5 volts to 0 volts. And so this is a 0. And here we have a transition from 0 to 5, so that's a 1. Here we have another transition from 5 volts to 0 volts. And then for this. And I believe it's named after I think it was, invented at the University of Manchester in the UK. And so Manchester coding is just an example of one of the simpler ways of combining clock and data into one signal so that the transmitter and receiver don't need perfectly synchronized clocks. This short interval here is drastically different than the regular interval that we see everywhere else, and so the receiver can just ignore this because it doesn't match the symbol rate. Even if the receiver's clock isn't completely perfect from 0 to 0. And this is again a transition from 5 volts to 0 volts, so that represents a 0. This represents a 1, a 0, a 1, a 1, 0, a 1. And then here you can again see those transitions from 5 volts to 0 volts. This is a 0, 0, 0, 0, 0. So very clearly there's 5 of those transitions, so we know there are 5 zeros. And then finally we have that transition from 0 volts to 5 volts, and that's a 1. So you might be wondering, what's going on like here, for example. We're transitioning from 0 volts to 5 volts, so shouldn't we like count this as a 1 in here? And so actually, we shouldn't, because there's still a clock, and we still expect to see Manchester coding is
Data dev. What's
just an example.
What's up? What's going on?
This video is about signal encoding of noise. Have a voltage transmittal of it.
मैनचेस्टर इनकोडिंग ओके तो मैनचेस्टर इनकोडिंग करने से पहले
Manchester encoding.
The problem with the Manchester encoding scheme is that it doubles the rate at which signal transitions are made on the link, which means that the receiver has half the time to detect each pulse of the signal. The rate at which the signal changes is called the link's baud rate. In the case of the Manchester encoding, the bit rate is half the baud rate, so the encoding is considered only 50% efficient. Keep in mind that if the receiver had been able to keep up with the faster baud rate required by the Manchester encoding in figure 25, then both NRZ and NRZI could have been able to transmit twice as many bits in the same time period.
This video is about signal encoding, specifically digital signal encoding. I've listed several encoding methods on the left here, and we have a sequence of bits up on top. I'm going to show you how to encode this bit sequence using each of these digital signal encoding methods. Now, the means that we have to encode these signals is via different voltage. Levels. So for each encoding method, I will draw a line indicating how the voltage level alternates as the encoded bit changes. The first method I'll be discussing is non-return to zero level. This method is pretty straightforward. It's more or less what you'd expect for encoding bits. We have one voltage level corresponding to 0, and another voltage level corresponding to 1. We'll actually be using a positive voltage level to correspond to a 0. So let's say that this is some positive voltage, and we have another 0, so we continue to have that positive voltage. But then when we encounter the 1, the voltage level drops down. And because we're using digital encoding methods, we have very sharp angular waves here. And now we have a lower voltage level to represent the 1. And the next one is that same level. And then we go up again for the 0, down for 1, up for 0, down for 1, and we stay down for this sequence of 1s, then up again at the end for some 0s, and then a final 1 at the end. So this is a straightforward encoding scheme. I can look at the signal and I know immediately that the high values are 0s and the low values are 1s. The next encoding method, non-return to 0 invert, is an example of a differential encoding method. With this encoding method, it is not immediately obvious which bit we are encoding simply by looking at the signal, because each bit we encode will depend on the preceding bits. So we have to have some sort of starting point for this. So we'll assume that we start at the lower voltage level, but every time we encounter a 1, we will change the voltage level. So I start at the low voltage level, I have a 0, so I stay at that level still, but then when I encounter a 1, the voltage level jumps, and it is this change in voltage level that indicates that a 1 is what is being encoded next. And then we have another 1 occurring, so we change the voltage level again. Next we have a 0, and we do not change the voltage level when we see a 0, but we have a 1 next, so we'll change and go up high. And then here we have a 0 again, so we'll stay high. And then we have a sequence of 3 1s, which means we'll be alternating back and forth. So this change encodes a 1, and this next change encodes a 1, and then this next change encodes the third 1. And then the 2 0s do not require a voltage level change. And then at the end we have a 1, which causes us to jump up, giving us this result here. And let me just emphasize again that we have 0s being encoded both with low voltage levels and here with high voltage levels. Similarly, this 1 has a high level and this one has a low level. So it isn't just the current voltage level that indicates what bit was being encoded, it's the whole history of the sequence that tells us what the current bit is. Differential encoding schemes like this one can be useful in the presence of noise, because detecting a voltage transition is usually easier than assuring that the voltage maintains a certain level. Both of these schemes require use of 2 distinct voltage levels. The next 2 schemes involve 3 voltage levels, essentially 0 ternary positions of this interval with a to prepare for the next signal that will be encoded. So for example, this 0 is encoded with a drop in voltage level in the middle of this interval. The next bit we will encode is also a 0, which means that the voltage level needs to rise up between intervals so that it can drop back down again to represent 0. Now the next bit we're encoding is a 1, which means we do not rise up between intervals. We simply maintain this lower voltage, and then the rise in voltage level occurs here in the middle of the interval. Similarly, to encode the next one, we must drop at the transition between intervals so that we can rise up again to represent the 1. So just remember that every 0 will have a downward transition in the middle of the interval, and every 1 will have an upward transition in the middle of the interval. So down for 0, and then up for 1, and then here, because we have another one coming up, we go down between intervals so that we can go up for the 1, and then down again between intervals, and then up for the 1, and then here we go down for 0, and then up in between, and then down for 0, and then finally up in the middle of the last interval to represent the 1. So Manchester is a scheme in which we can tell exactly which bit is being encoded simply by noting which direction the transition is in the middle of the interval. We can ignore the transitions between intervals when we are decoding the signal. Of course, the sender has to make sure that it accounts for those transitions so that we'll be at the right starting point for each interval. Differential Manchester
A final encoding that we consider, called 4B5B, attempts to address the inefficiency of the Manchester encoding without suffering from the problem of having extended durations of high or low signals. The idea of 4B5B is to insert extra bits into the bit stream so as to break up long sequences of zeros or ones. Specifically, every 4 bits of actual data are encoded in a 5-bit code that is then transmitted to the receiver, hence the name 4B5B. The 5-bit codes are selected in such a way that each one has no more than 1 leading 0 and no more than 2 trailing zeros. Thus, when sent back to back, no pair of 5-bit codes results in more than 3 consecutive zeros being transmitted. The resulting 5-bit codes are then transmitted using the NRZI encoding, which explains why the code is only concerned about consecutive zeros. NRZI already solves the problem of consecutive ones. Note that the 4B5B encoding results in 80% efficiency.
Hello friends, welcome to another tutorial in the
Hello friends,
In this tutorial, we'll talk about an encoding scheme which is not very popular but has its own importance, and the name of that encoding scheme is 4B 5B encoding. In this tutorial, we'll talk about the definition and usage, the advantages of this encoding scheme. We'll see the input-output truth table, and we'll do a numerical based on this encoding scheme. Now, this encoding scheme takes a 4-bit input and generates a 5-bit output. So with 4 bits of input, we could have 16 possible combinations that I've written here. And for each of the possible input value at the encoder, the output is uniquely defined as in the table. Now this table is taken from Wikipedia. I do not know the rationale behind generation of the output of the encoder, but the fact of the matter is for a 4-bit input, for example 0000, this code is encoded into a 5-bit output code, which is 11110. Now the reason why we do that is pretty simple. Now if you look at the output set, which is a 5-bit code, you'll never find 3 zeros in a row. Now the main objective of encoding is to avoid long strings of zeros, as we mentioned in HDB3 code and other codes where timing extraction becomes a problem. So a long string of zeros could result in misinterpretation of a 0 DC voltage at the receiver, so that is avoided here. Now if you look further closely, the last two strings are at most 0.
Yo, Montel Logic.
0.
What's up?
So I have a 0 0 here and a 0 0 here only. And the first string is at most 1 0. So even if you combine two input codes, then you'll never get a string of zeros greater than 3. I'll show you. You that with an example. The basic definition. So if into at the one can so
So today we're talking about C and video, but let's just say that C++ compiler, the tool. Look at this line of code. Is it C or is it C++? Well, it doesn't matter. As long as we don't invite little C++ to the conversation, this code is perfectly fine. You standard variant. Come to think of it, C functions. All this exam here, we get as long. Well, good community can see you are now in contravention of the little C++ community. As long as you're a legal C++ community, I fully expect to hear